Although we've been assuming we're using batteries for our circuits so far, we know that most of the electrical energy we use comes from the wall. Batteries give us a steady voltage that doesn't really change until they're all used up and it drops down below the usable level or all the way down to zero. This is DC or direct current. Wall outlets give us AC or alternating current. If we had a voltmeter that could react quickly enough and we could read it quickly enough, and we put the leads into opposite sides of a wall outlet, we'd see the voltage difference between the two sides go up to about 170 volts, back down to negative 170 volts, and then back up. This would all happen in a 60th of a second. If we were in Europe, it would take a 50th of a second. If we made a plot of the voltage readings, it would look like this, a sine wave centered around zero. This AC source, instead of looking like the long bar and short bar, it looks like a sine wave inside a circle. So this is a resistor plugged into the wall outlet. This is what a toaster looks like, basically something that would heat water. Any simple device that's just made to produce heat from the wall outlet would look pretty much like this. Now, of course, in reality, it might have an on-off switch, a fan, a thermostat, but this is the main idea. Now, just like with the battery-powered circuit, we could say, well, what's the current through the resistor? The voltage is always changing, so according to V equals IR, the current is always changing. If we plotted current against time, it would look just exactly like this, only we'd have different units on the y-axis. What about the power used by the heater? Well, if we use P equals IV, each one of these is some number times a sine wave. If we multiply sine times sine, we get sine squared. Sine squared looks like this. Notice it's never negative. It can drop to zero, but it can't be negative. This makes sense because we know there's no time the power company is absorbing power from your toaster. That's not allowed by physics. If we did a plot of power used versus time, we'd get this. And again, these peaks are on in this case, this is 120th of a second for this cycle to happen. So if we had a high-speed camera, and there are phones that will do over 1,000 frames per second now, you could look at something like a toaster or one of the old kind of incandescent light bulbs that works by getting hot. If you videoed it with the high-speed phone and then replayed it frame by frame, you would see the filaments get lighter and darker because you could actually see this happening. Now, a reasonable question is, what's the rate of energy being dissipated in the resistor? It's easy enough to say V squared over R just like it was before, but what value of V should we use? We can't use the largest value because the voltage is only 170 volts for a tiny fraction of a second. We can't average the voltage because the sine wave is above zero exactly as much as it's below zero. So if we averaged it, we'd get zero, and we know your toaster doesn't operate for free. If we could find the average using calculus, which of course we're not going to do, or you could imagine you print out this plot and cut off the tops at the right size to fill in the valleys. That height of the resulting rectangle would give you your average, and it would actually be right here at 0.5. So it's 1/2 the maximum. This means we could say the power we're using, that toaster is using, is Vmax squared over 2R, where Vmax is our 170 volts, our largest value. Unfortunately, now we have two power formulas. We've got V squared over R for a battery and Vmax squared over 2R for the wall. And that's kind of a pain. A way to get around this is to come up with a new kind of voltage measurement instead of just looking at the peak. And it's going to have this weird name, and it's going to be reflective of the fact that we're going to split this factor of 1/2 into two pieces. We're going to call it the root mean square voltage. The reason we have this weird name, we know we can't average the sine wave. We can square it and average those numbers. Of course, that's going to give us volts squared instead of volts, so we then have to take the square root of the average. That's where we get the name root mean square. It's like the reverse of the operations we're doing. Anyway, this new kind of voltage is pretty simply just the max voltage divided by square root of 2. Now, what do we get if we do VRMS squared over R? Well, VRMS squared over R is Vmax squared over 2R. So this gives us the right answer. In other words, this VRMS tells us what size battery do we need to be equivalent to the 170 volt up and down fluctuations of the wall outlets. And what we find out, if we do 170 divided by square root of 2, we get about 120. That's the reason we refer to wall outlets as 120 volts. That's their RMS voltage value. We can do the same kind of definition with current. Current is also going to be a sine wave. We can look at whatever the maximum value of the current is, Imax, and define a root mean square current as that maximum current divided by square root of 2. Now what's our power formula? We had P equals IV when we were talking about batteries. If we want to talk about voltage and current in an AC circuit, we could do their max values divided by 2, which again is a pain. Now we got to learn a new formula. Or we could just use their RMS values. Each one brings in this factor of square root of 2 on the bottom, so it takes care of that 2. So this is why we like the RMS values of voltage and current. It makes life easier, and we can use the same formulas that we've already learned. Now, why is AC such a big deal? Well, it's what comes out of a generator, and we'll see that in a few chapters, but the bigger reason is related to the fact that the power dissipated by a resistor is proportional to the square of the current. The power line to your house, which is actually 240 volts, that's what your water heater and your stove and air conditioner run on. Imagine that line was directly connected to the power plant generator. If the power plant is a 1 gigawatt nuclear plant, which we have, then the current leaving that nuclear facility, we got to get 1 billion watts out at 240 volts. That means over 4 million amps, which is a ridiculous amount of current. Even if the wire that was coming out of the power plant was so short and so thick that its resistance is a milliohm, which is ridiculously small, the power burned up heating up this wire would be IRMS squared R, 16 gigawatts. In other words, more than this thing is making. There's no way we could send this out on any reasonably sized wire. All it would do was vaporize the transmission lines. You'd never get any power at your house. So there are a few solutions. One is, instead of a relatively small number of these giant gigawatt scale power plants, we could have a bunch of small ones, and there's basically going to be a power plant for every neighborhood. This probably doesn't sound very good, certainly not for your property values, but imagine the power plants are still all powered by coal. You really don't want to have that in your neighborhood. We could have the power plant send the power out at higher voltage, which means lower current. If we send it out at 100,000 volts, the current drops to 10,000 amps, that's still a lot of power, but now there'll actually be some left when it gets to you through the transmission lines. What's the downside of this? Well, if at your house you're getting power at 100,000 volts, your outlets are going to be sparking. The dielectric breakdown of air that we talked about will be happening all the time. Also, all your appliances, their cords, the motors are going to be enormous because they're going to be filled with insulating material. The current carrying wires could be like bread twists, but you're going to need a fire hose amount of rubber on the outside of that to insulate it. And besides all that, a shock is pretty much guaranteed to be fatal if you're talking about a connection to the power plant at 100,000 volts. So our solution is we use AC and the fact that it can be transformed. This is practically magic. We have a hunk of iron, we wrap some wires around it, and we can make current go up while voltage goes down, and vice versa. This is a lot like an electrical version of a lever. A lever will let you exert way more force than you could otherwise, but what you trade for that is you have to move the lever a lot more than the device that you're trying to lift will move. Same as jacking up a car. Yes, you're able to lift a car with one hand, but that hand has to go up and down 100 times before the car goes up 20 centimeters. Now, transformers aren't 100% efficient, but the big ones can be 99% or better, so they're almost perfect. The way the power grid actually works is the generator to power plant typically is making power at a few thousand volts and lots of amps. It goes from there immediately into a transformer, and the voltage gets stepped way up. It could be as high as 1,000,000 volts, which they use in China, but in the US, about the max we use is around 765,000 volts. So the output current is very small. That means the transmission losses are very small. When the power gets to a city, it steps down at a substation. You'll see these as weird yards full of electrical equipment and big chain link fences around them. Usually gets knocked down to something like 15,000 volts, and then this runs through the city and gets stepped down again close to your house. The transformers for these, it looks like either a big cylindrical trash can on a telephone pole, or if you've got underground power, you've got green cubes that are about a meter on a side in maybe every other yard. This is the best possible situation. We've got giant power plants, which are more efficient. They're far away from where we live, but they can supply lots and lots of homes and businesses without wasting all that power heating up the lines. DC won't go through a transformer, so this is the reason the power grid works like it does. It's why we have AC instead of DC for power distribution.